Modern communication networks suppose fast path restoration mechanisms which allow to reroute traffic in case of link failures in a completely decentralized manner. In this work, we address the computational problem of finding a set of replacement paths that can be used in certain link failure scenarios. Real-time traffic often requires sub 50 milliseconds restoration. This means the traffic cannot wait until the entire network updates its global view of the new topology. In order to achieve this, routers employ local mechanisms known as fast rerouting (FRR). The idea of fast rerouting is to forward packets as soon as failure is detected on the link to the next hop. This is done using only locally available information, including packet headers and the fade link, preferably without storing failure information onto the packet's header. In addition to being limited only to local information, we would like to have a resiliency that matches graph connectivity. Moreover, we would like to preserve visits to nodes on the original path. That is the path if no failure occurs. Some of those nodes may be network function waypoints and packets are required to visit them. Let's see the restoration mechanism in a simple example. Our packet starts at node S and is destined to node T. The link ST is not available, the link A. Node S notices this and activates the fast rerouting mechanism. Node S reroutes the packet via the path SWT or the link B. This fast rerouting mechanism is already in use in today's ISPs and is known as TILFA, Topology Independent Loop-Free Alternate. As long as no more than a single failure occurs, TILFA guarantees reachability. That is, any backup path assignment works here. But what about more failures? What if also the link B fails? Then certainly the backup path SWT wouldn't be usable. Now the question is, what should be the backup path of the link B itself? This means that TILFA is not designed to handle double failures. Its main focus is to cover resiliency for all links, which was a shortcoming in its precursor version called LFA, where full coverage was subject to network topology or graph structure. TILFA does the same for all link full coverage, independent of the graph structure. We push the idea forward by introducing backup path schemes that tolerate beyond single failure scenarios. Consider the same scenario. Packet starts at node S and is destined to node T. The link A is not available and packet is forwarded to node W to be then forwarded to T. Notice that the link A is the shortest path from S to T, and this shortest path is not available. Therefore, node S forwards the packet to node W. to be then forwarded to T via B. The dashed green line represents the backup path of link A. Now the packet is at node W and experiences failure on link B. In this moment, node W activates the backup path of link B, which is the path WST, which goes via link A. As a result, node S and W forward the packet to each other, and the packet is trapped in an infinite forwarding loop. In reality, the packet gets dropped after a few times bouncing between the two nodes, but we need to prevent this as far as possible. So TILFA does not guarantee two resiliency for this reason. This situation is happening because the backup path assignment makes the two links A and B mutually dependent. If only one fails, the other is an option, but if both links fails, we get a forwarding loop. Therefore, a cycle of two dependencies, in this case between links A and B, implies that the backup path scheme does not tolerate more than one failed links, or it is one resilient. Now let's see a two resilient backup path assignment. Same scenario, the packet starts at S, is destined to T. Link A is not available and the packet is rerouted along the backup path via link C. The packet arrives at node N and experiences another failure, the link C. Node N activates the fast rerouting mechanism and reroutes using backup path of link C, which goes through link B. If link B is failed as well, we have the same forwarding loop problem. Therefore, we cannot guarantee reachability under more than two failures. But with this backup path assignment, we can handle two failures. This is already good enough for this example, since the graph is not even two connected. The observation from this example is that when the shortest cycle of dependencies has at least 3 arcs, the backup path scheme is too resilient. There is always a third link in any COD that restores the connectivity in case of up to 2 failures. The question is, can we get full coverage? Not in this example, because the graph is not too connected, to edge connected. This is only for simplicity of the illustration, and it is easy to make this graph a two connected graph by adding few more links. Now let's see the same problem more formally to make sure we are on the same page. We are given an f+1 edge connected graph, and the task is to compute a backup path scheme. Recall that a backup path scheme is just an assignment of replacement path to links. We want a backup path scheme that assigns a backup path to all links, and we desire a maximally resilient scheme, which would be a F-resilient scheme. As a side note, it is still an open question whether F-resilient schemes exist for every f+1 connected graph or not. Next, I will show you a maximally resilient backup path scheme for the class of complete graphs. It is very simple. For each link ij where I and j are not the node 0, the backup path is simply ij+1, 0, i+1j. For links incident to node 0, such as 0j, the backup path is 0j+1j. This scheme is n-2 resilient, which is maximally resilient because the complete graph of n nodes is n-1 connected, and a resiliency that is one less than connectivity is a maximal resiliency. The proof is not trivial, and all details can be found in the paper. The major contribution in this paper are schemes for generalized hypercube. Generalized hypercube is the Cartesian product of complete graphs. It generalizes binary hypercube. A binary hypercube is simply the Cartesian product of complete graphs of only two nodes, which is basically a single edge. The construction of the scheme is not intuitive and rather complex, so it is skipped in this presentation due to time and space constraints. The model that we consider in our work has been considered in some old papers. However, this work, and in particular its precursor, which addresses the binary hypercube, is the first one with a rigorous analysis of resiliency. There are, however, different but related models, such as arborescence routing. In arborescence routing, upon a link failure, the packet is rerouted along a pre-selected tree routed at the destination. In our model, the packet circumvents the failed link and continues from the other endpoint of the link towards the destination. Perfect resiliency is another related topic and is a stronger notion of resiliency. Its objective is to deliver the packet to the destination as long as any path to the destination exists. Since such resiliency is ideal or perfect, it is not always feasible even on a simple structure like K5, which is the complete graph of 5 nodes. Whereas in our model, a simple backup path scheme exists with resiliency up to connectivity or maximal resiliency for complete graphs. All complete graphs. There are other models that require writing non-standard headers onto the packet's header. Our model only requires headers that are necessary to realize a backup path scheme. The standard segment routing can perform this task already very well. However, segment routing comes with a natural limitation, which is the maximum number of segments that can be pushed into the packet label stack header. In our work, we relaxed this segment routing restriction and assumed unlimited number of segments. We leave this optimization as an interesting open direction for future works. Lastly, perhaps the most intriguing question is whether connectivity is also a sufficient condition for maximal resiliency. Even observing some small but non-trivial resiliency on arbitrary graphs with arbitrary structures would be very interesting. Thank you.